Welcome everyone. We're just gonna let everybody in and then we'll start. Okay. So I'm gonna start with introductions. Welcome again to VSET. So this week we have Alex Smolin from Toulouse, and he's talking to us about information design and smooth games, which is joint work with Takuro Yamashita. We also have guest panelists here, Mallesh and Fedor Sandomirskiy. I'll just remind you that this is an hour talk with 15 minutes at the end for questions. Also next week, we have Michelle Muller-Itten from Sangala, and she'll talk to us about rationing attention via ignorance equivalence. So join us next week for that. Without further ado, this is recorded. Yes, I need to remind everyone of that. But without further ado, Alex, please get us started.
Thank you, Francesco. Thank you for inviting me. Thank you, Mallesh and Fedor, for agreeing to be panelists, and thank you everyone else who willing to attend it. So I would like to talk about my work, information design in smooth games, which is joined with Takuro Yamashita, who was my colleague here in Toulouse, but now he moved back in Japan. And let me start with a little bit of a bigger picture, how we started thinking about this project. If you can think about economic context, information asymmetries are ubiquitous in economic settings. We all know that it has been in syllabus, economic syllabus for a long time, but more recently, data collection and information control becoming a more widespread in the economy, partially because of the development of advanced information technologies, and in particular, artificial intelligence more recently. And as a result, there are technological giants like Amazon, Facebook, Google, who shape strategic interaction at the unprecedented scale. And many of these companies face the explicit choice over different information policies, that they must decide what information to provide to the users, and these choices will obviously be affecting the choices of the strategic users. Now, I think partially as a response to these developments in economic theory, there has been a recent and rapidly growing field of information design and Bayesian persuasion. And as many of you know, the standard setting in this literature is that there is a designer that has control over information available to players in a game, and this designer is not restricted by anything but statistical possibility in how she can provide information. Now, the existing literature, I think, does a pretty good job at providing the general methodology, how to think about this problem. We think about information structure as a joint distribution of signals and states. We can pose formal maximization problem as maximizing the principal subjective over this possible information structure. And there exist several general principles of how to approach solving these problems. However, to the best of my knowledge, most solutions are actually currently known only in the games of what I would call small scale. That is, either it is a single player, so that it's not even a game, it's basically a decision problem, and this is there within a few pair specification. So this is basically Bayesian persuasion literature. Or it is a proper game between many players, but most of the papers that analyze that case focus on binary state or action. In particular, I think there is a lack of solutions in large-scale economic settings, that is, settings with many players, continuous and possibly multidimensional state, and importantly, continuous actions. And these are standard economic settings that we use otherwise in economic framework. And also, these are settings which are natural in applications. So I think it's useful to understand how solutions in these settings look like. And this is exactly where our contribution lies. In particular, we develop a tractable solution method for large-scale information design problems. This method is based on dual certification of optimal information structure. In particular, we will show that the information structure is optimal if it is jointly implementable by information and by incentive. And that will become clear what it means later in the talk. But with this method, we show that it's actually quite tractable, and we can solve several novel and interesting applications. In particular, polarizing expectations, persuading investment, and informing a marketplace. In this talk, I will focus primarily on polarizing expectations and informing the marketplace. And as a common theme in solving these applications, they emerge optimality of two classes of distinct information structures. One class is what we call targeted disclosure. This is an information structure that provides full information to some subset of players and provides no information to all other players. And another class of structures is Gaussian information structures. These are the structures under which the signals that you send to the players are jointly normally distributed. And we show that these simple and natural information structures turns out to be exactly optimal in many natural environments. And a little bit as a side product of our analysis, we're actually able to establish robustness and uniqueness of optimal information structures. But I will elaborate on it in particular applications. So this is kind of overall view. And unless there are exact questions, let me go into the model so we see exactly what I'm talking about. And the model is fairly standard information design problem. So there are n players, finitely many, indexed by I and a designer. There is a state, omega, possibly multidimensional, which is distributed according to a commonly known prior distribution mu0. Each player decides whether to take which action to take, and this action is AI. For now, it can be anywhere in the real line. In paper, we have extension that can allow to handle bounded actions. You can also possibly think about multidimensional actions. I think it's all should be doable. Denote by capital I the set of all possible action profiles, that is vector of actions for each player. And the exposed pairs of player I and of the designer are respectively UI and B. And importantly, so this could be general functions, but importantly, both of those can depend on the action profile taken by the players and on the state, right? So what the designer can do, the information designer, the designer can choose an arbitrary information structure with private signals. That is, this information structure basically a tuple of f and pi. S captures the possible signal realization that the players can observe, and pi gives meaning to these messages, right? So the pi is a joint distribution between states and signals that has mu0 as a state marginal distribution. And you can see that this information structure can be arbitrary, and it can inform about the state, but it can also send private signals or possibly correlated to different players. Now, any fixed information structure induces a game of incomplete information and is evaluated by the expected designer's payoff in a designer-preferred Bayes-Nash equilibrium. That is, if there are multiple equilibria, as fairly standard in many mechanism design applications, we will assume that the designer can basically lead the players on playing preferred equilibrium. In some sense, it's a natural focal equilibrium because the design information will actually come in form of recommendations. But also in many of our applications, it turns out that under an optimal information structure, the equilibrium is unique. So the multiplicity of equilibrium will not even be a concern.
Can I ask a
yes.
quick question?
Yes.
Because you mentioned Gaussian information, is it important that the set omega is unbounded or not?
Very good. So
can it be an interval? The state could be.
Yes. In anything. There is a lack in connection, I think, but I think I understood your question. So your question is what can be the state? And the answer is state can be anything. We do not need to require any assumptions on the state for our approach to work. Now, for example, it can be binary in principle. However, in our applications that we will use, in one application, we will not need any distribution of omega, but for Gaussian distribution, indeed, the fact the state is normally distributed will turn out to be will give us tractability necessary to solve the problem. So in those settings, we would like to have state unbounded, and this is why we allow for unbounded state, but it doesn't have to be unbounded. Absolutely, it can be binary. Yes, thank you for clarification. And the goal of our goal is to characterize an optimal information structure, right? That is the one, that maximizes basically expected designer's payoff. So this is all fairly standard, but let me just briefly highlight what kind of economic trade-offs are involved in this problem. So what information control allows the designer to do, first, it allows to inform about the state, perhaps partially. And this is important because both players and the designer care about the state. And second, which kind of comes coupled here in this information control, it also allows the designer to coordinate or miscoordinate players' actions, because these individual signals can be arbitrarily correlated. Now, this is what you can do. Now, challenges in solving such a problem, there are several, but I think the first one is that, in the Bayesian persuasion literature with a single agent, a very common approach is belief-based, which leads to concretization, right? Is the approach where we think about what splits of beliefs we can induce, and then we optimize over these possible splits of beliefs. And this is possible because the posterior belief about the state is a sufficient statistic for the agent's behavior when there is a single agent. Now, when we have multiple players, not only each individual's belief about the state matters in general, but their belief what others believe about the state, what you believe, what they believe, what you believe about the state, etc. Right? So the whole belief hierarchy matters, and maximizing solving this problem in a space of belief hierarchies is notoriously difficult. So Matthew, Perega, and Tanya have a very nice paper when they discuss it. They have some examples, but quite generally, this is quite a hard approach to use. Now, there is another approach, which I think in games often is more tractable, which is basically goes back to Meyerson, but recently were put forward by Bergam and Morris. And this is action-based approach, not belief-based approach, but action-based. And basically observation that we care about beliefs only insofar they affect players' actions. So you can think about the direct structures that recommend actions. And then you maximize over these direct recommendation information structures subject to incentive constraint. Now, in our large-scale setting, given that we think about continuum of actions, that approach, the challenge of that approach is that there are many possible actions you can recommend, and there are many incentives you need to keep track of, because the player, in principle, can deviate to any of her possible actions. So this is a challenge, but nevertheless, we make this approach work, the second one. But for that, we need only one substantive assumption, which we later will discuss, that we can even relax. And this is assumption of a concave game. So what is that? Is the assumption that for each player, for each state, and for each action profile of all other players, the individual payoff of each player is continuously differentiable in her own action, strictly concave in her own action, and obtains its maximum at some finite value. So basically what this assumption buys us is that it allows to capture incentives through first-order conditions, which is very fairly natural for economists to have. In particular, for any belief each player might have about the actions of the others and about the state, the best response of each player can be found as a unique solution to the first-order condition, which in our setting basically boils down to the expectation of the marginal payoff of each agent equal to 0. And the equilibrium play will be characterized now by a system of such conditions. That is, whenever you recommend particular action, this condition should be satisfied.
Alex?
Yes.
Alex?
Yes, please.
You mentioned that in your setting, the equilibrium is typically unique or is often unique. But is it true that actually the strict concavity implies that given the information structure, it is always unique, or there are exceptions?
Yes, What we show is that in our applications, in several of our applications, under an optimal information structure, an equilibrium best response is unique. So the equilibrium is unique. However, in general, even though we have a concave game, it is not necessarily true that the equilibrium will be unique, simply because there is a lot of room how you can play with information. And so in fact, actually, even solving for an equilibrium for some strange information structure may be intractable often. But what we show that actually you can bypass this problem by solving for equilibrium for any information structure and characterize optimal information structure nevertheless in many applications. But yes, it's a great question. So even though it's a concave, in your own action, it doesn't. It's still very rich in a sense, because in particular, let me also highlight that we do not require any restrictions on the designer's objective, which will affect which information structure will emerge optimally, or the player's payoff with respect to the actions of the others of the state. In particular, they might very well be even discontinuous. So the only thing that we need to require that if you know the actions of the state, then you can find your best response via first order condition. That's all what we need. And at the end, I will discuss also how we can relax it, because basically in concave game, these first order conditions are necessary and sufficient to find equilibrium now and to ensure incentive compatibility. Now, in a general smooth game, it will be necessary but not sufficient. But still, we can apply our approach, and I will discuss it later. Okay, great. So, but for now, let's keep this assumption in mind. And okay, so far it can be quite abstract. So let's go into one particular very simple example so everybody is on the same page. Because I think it's also then later we will illustrate how we apply our approach to that. So think about a very simple and stylized game of polarizing expectations. In this game, there are even number of players, and 2, 4, 6, etc., and one-dimensional state. Right? It can be binary, for example. Or it can be take 3 values. Each player aims to predict the state. So the action of each player is the prediction on the real line, and the payoff of each player is simply the difference between their action and the state. So in some sense, it's not even a strategic interaction. So each player simply wants to predict the state, and as we all know, in this environment, for any belief that the player might have, the best response will be the posterior expectation of the state. So basically, this game is a way of capturing what kind of distributions of posterior expectations you might induce and how to maximize over them. Now, these are separate problems for different players, but they all come together through the objective of the designer. In particular, we will think about designer who aims to polarize players' predictions. Her ex-post payoff is simply pairwise square difference between predictions of individual players. Right, so captured by that. So this is in some sense a measure of polarization, of belief expectation polarization in society, and we would like to find information structure that polarizes this, maximizes this polarization that captures by this formula. Why we care about this objective? Well, first of all, maybe there is some party who wants to polarize society, and what kind of policy that party should do, that we will give a solution. Second, motivation for this objective, which I like even more, is more metaphorical, right? Because basically, by doing this exercise, we will identify the limits of maximal Bayesian expectation polarization, right? Because if you think about recently, there has been this anecdotal evidence that society becomes more polarized in terms of beliefs and opinions, even though they get more and more easier access to information. And there are many possible speculations or explanations why this is happening, if it is happening. But basically, you can split these explanations in 2 parts. One is purely rational and Bayesian. So they all start with the same prior, but they diverge in their opinions simply because they attend to different informations. You read different news, you learn about different facts, you talk to different people, but you're perfectly rational nevertheless. A second trend is add some behavioral explanation into the into this. For example, you can think about echo chambers where the people they simply talk to each other repeatedly, and and they become more convinced in their own opinions, even though it might be not rational from a Bayesian perspective. And basically what this exercise allows us to do is to allow us to identify how maximally you can possibly polarize the society captured by this index via purely Bayesian source. And if the society happens to be polarized more than that, then it cannot be Bayesian. I mean, this is, in some sense, one way to think about this sort of exercise. Yes, so now, so this is kind of the question. I mean, it's also a curious theoretical question, right? How to think about it. So, because think how to polarize these expectations, and once you start thinking about it, there are several forces or conclusions that you might have. So first, it's fairly straightforward that any public information structure, including no information and full information, will lead to the same predictions, right? If you provide the same information to everyone, then they will all have the same predictions, and there will be no polarization at all. In fact, it's the worst thing you can do as a designer. So it includes no information and full information. So that means that to polarize predictions, you as a designer should provide some imperfect information and in a heterogeneous fashion. But the question is how? And how does the solution depend on the distribution of the state, in particular, whether it matters whether the state is binary or it's distributed on an interval or it's unbounded, and how it depends on the number of players. And yes, and I'll let you think a little bit about this question, because I will let you form your own conjectures over the next 5-10 minutes. And then I will go now into the more general approach, how we solve it, how we solve the problems like that. And after that, I will apply it and give you a solution to this problem. But I will let you move over it and form your own conjectures, because you can think, yes, you can partition the state, right? You can have different partitions for different players. But you can also, for example, send negatively correlated signals. So there are many things you can do. How to do that optimally? I'll let you think. And myself, I will proceed to the general solution. Okay, because I hope that application gives you enough motivation to be interested in this kind of tools. And because what we will develop now will allow to solve the previous question basically in 2 slides. Okay, so now to our general solution method. What we do, we build on the duality methodology, which is of course routinely used in mechanism design. We're not inventors of duality methodology. And in particular, it has been applied to delegation, to robust cell settings, to matching, and perhaps more importantly, recently it has been applied to Bayesian persuasion information design settings. And I think the best way to position ourselves relative to existing papers is as follows. So what we basically do, we extend the continuous action machinery of Kolotilin and Kolotilin-Korau-Wolitsky from a single player and one-dimensional state to multiple players in an arbitrary state space. So because what these 2 papers do, they study the analog of our basically problem, in which there is a single player, so it's a persuasion question, and there is one-dimensional state, and they also require some additional single crossing conditions on the preferences. And they apply duality machinery to that. But importantly, they build on this continuous action first order approach. So what we show that very similar approach actually works very nicely with multiple players and an arbitrary state space. And this approach allows to find very nice and natural solutions in natural applications. In particular, the applications that we find are tractable, and they go beyond the discrete action framework of Galperti, Levkon, and Perego. Because these guys, they studied games, but they studied games with discrete action, and they applied duality machinery to discrete actions. But because they have discrete actions, they need to keep track in generally. They do not impose additional concave structures, so they need to keep track of many incentive constraints, and as a result, both the primal and dual problems are different. So they do not obtain the solutions that we have.
Sorry, could I be just the could I speak up in favor of discreteness?
So yes, I love discreteness. Yes, but go ahead. Yes.
No, I mean, I'm just wondering, like, if you're phrasing it that way, and maybe this is a question you want to leave till later. But I mean, per se, generalization to continuity is not useful, right? So is it that the continuity coupled with the concave assumptions is giving you some nice analytical results, or how should I think? Yeah, okay.
Exactly. It's just more tractable, because it's not just continuity; it's importantly concavity and the fact that this first order condition captures the incentives. I mean, this is why first order approach is tractable in economics. Basically, and it allows us to analyze applications which go beyond Galperti, Levkon, and Perego. Think about belief expectation polarization example that they just gave. If you can form only discrete the belief polarizations, it's clearly restrictive, and you will not get the solutions that we get. Right. So, and it's exactly just tractable. And this is why I highlight these tractable solutions. But I would like to highlight that both primal and dual problems are different from Galperti, Levkon, and Perego. Just because they have different incentive constraints, that they're different problems. So in this sense, I think we are a bit closer to Kotin and Karawalinski. Okay, great. So with this in mind, how to position the paper, let's look what the problem is. So what the approach is, and the information, because it's actually quite tractable, and I hope that after this talk you will get an impression that is actually useful, and you can start applying it to many applications that you might have in mind. So the information design problem can be stated as maximization over direct information structures, right? This goes back to Meyerson, and that recommends action subject to two sets of conditions. First is that the players are obedient, right? The players are willing to follow recommendations, and in concave games, it is captured by first order conditions. And second, by the statistical feasibility of the information structure. This is standard. Now, in our setting, basically, what it will boil down to mathematically is this, right? So the problem is to maximize over the set of direct measures, which is basically joint distributions over actions and states of the ex ante payoff of the designer, right? Given that all players will be willing to follow recommendation, subject to two sets of constraints. Let's start with feasibility. Feasibility basically requires that the projection on the state space equal to the marginal, and the obedience basically requires that the projection of this expected marginal payoff is equal to 0. And this is the correct analog of that condition expectation of your marginal payoff equal to 0, given that we have continual actions. Now, it's problem that is fairly easy to write down. Now, how to solve that? It's less clear because there are so many constraints and the object is reached. However, the useful thing, which of course was observed already by Meyerson, that the problem is linear. The problem is linear in pi. Pi enters both affects linearly the objective and all of the constraints. Because of that, we can appeal to duality methodology and construct the dual problem. And that's what we will do. So what we will formulate a dual problem and simplify it into an adversarial contracting problem. So there is one intermediate step that I would keep because it's fairly technical and it's not, I think, useful for most of the people. But there is a step which is missing. So it's not standard dual problem that I'm showing to you. There's some simplification that we've done. And basically, this is a problem which is very fairly, I think, to understand by economists. Because it turns out that this dual problem can be interpreted as adversarial contracting. And I will tell you then now interpretation. Forget about information design problem. Think about completely different problem where there is a single principal and a single agent. Single agent, not many players, but one agent who, first of all, who has full access to the state, and second, who can control actions of all players in the game. So this is the agent who can fully control this n-dimensional allocation. Now, this is a contracting problem, meaning that you cannot affect information on the agent, but you can affect his incentives. In particular, the principal can design a contract, lambda, that will affect the agent's payoff in this way. Now, why this way? Well, this comes because this is basically the version of a Lagrangian, plus some simplifications that I needed. But basically, you can see that this is the weighted average between the designer's objective and the marginal payoffs of individual players weighted by these contract functions, which is an object of the contract design in this problem. And the idea is that the principal aims to actually minimize the ex-ante agent's payoff. Because in primal we want to maximize, it's natural that in dual we want to minimize. But the conceptually it's incentive problem. So it's a standard in some sense contracting problem conceptually that you use a principle, you choose a contract, you have some objective. In this case, you want to minimize the agent's payoff. And then the agent, you know the agent will observe the state and will take the action which maximizes his own payoff. So the dual problem can be written as follows: minimize over this set of possible contracts this ex-ante agent's payoff. What is it? You average over all possible states with their respective prior. In each state, the agent with observed omega n will maximize over all possible actions her payoff, this V. So this is basically the dual adversarial contracting problem, which turns out to be important. Why? I will show you on in 2 slides.
So Alex, I'm sorry,
Yes.
I'm not following. Possibly this is a stupid question, but I think you're claiming that W is the agent's payoff in this setting, right?
Yes, it's defined as the agent's payoff. Exactly.
So this is so this is this fictitious agent that
Exactly.
has this weird payoff. He's got the same payoff as the principal, but he's discounting. Okay, fair enough. Okay.
Yeah. So that is
okay.
it. Exactly. And you as a principal in this new problem, you want to minimize this payoff of the agent example. That is it. So it's a fictitious agent. But I find it helpful to think of it in these economic terms of incentivizing these agents to do something, because I will talk about what it means to implementable by incentives. So on the next slide. And this dual problem is important for optimal certification. I will give you just 2 preliminary definitions which are standard, and I will give you the main result. First, say that this measure is implementable by information if it just satisfies the constraint of the primal information design problem. Meaning that if you recommend the actions according to the structure, it's feasible and obedient. This is clearly the prerequisite for the information structure to be optimal. It should actually be feasible. Second, say that the measure is implementable by incentive in a dual problem. Basically, if it can be induced by some contract in a dual adversarial contracting problem. That is, there exists a contract such that the dual agent will be observing the state, taking the optimal actions in different states, and that best response will generate this measure. So this is just a question of implementability here by incentive. Right? So we have these 2 concepts, and this is why all this comes together because of this theory. because the theorem states that if the same measure is implementable both by information and by incentive, then this measure actually is optimal in the information design problem. And the contract that implements this measure by incentive is optimal in the adversarial contracting problem. Now, notice how much simpler it is to check that something is implementable by information by incentive. You simply need to construct the contract that implements this measure and to see whether, if you recommend this measure, they will be able to follow recommendations. So prerequisite of this theorem is very easy to check. And then if it happens that it is implementable, then all of a sudden you actually prove optimality. So you don't need to check any other possible information structures. And so this is the power of this kind of duality machinery. And I will show you how we can use it in applications. But the argument behind this theorem is actually fairly standard in some sense, because under the conditions of this theorem, it so happens, you can fairly easily to show it, that the primal objective under this measure will be equal to the dual objective under the contract that implements pi. So if this measure is implementable by information by incentive, it must be that the maximum value that you achieve in a primal, which you try to maximize, is greater or equal than the minimal value that you can achieve in a dual problem. However, by weak duality, the value of the primal problem must be less or equal to the value of the dual problem. And this is basically what requires proof, but the proof is standard, fairly standard. And this is basically how the dual problem is constructed. This is why we have that dual problem like that. But consequence of these two inequalities, we will have that the values of the primal and the dual problem are equal to each other, and the optimal values are exactly obtained by pi and lambda. So solutions to the problems exist, and the values are equal to each other. So in this case, we will say that the contract lambda certifies optimality of pi, because the contract shows that in the dual problem, it implements pi by incentives.
Alex, I'm sorry, I'm slow, so I'm just trying to understand, because I'm a little bit confused about the way the theorem is worded and
yes.
the things below, which seems to be the proof. So the problem that we have is that the primal is very difficult to solve, right?
Yes.
In principle. So what we're going to do is we're going to focus on the dual, and we're going to find an information structure. Suppose that we find a solution lambda to the dual. That solution lambda will correspond to a pi, correct?
Okay. Yes.
So what you have here below the statement of the theorem is basically a proof that if lambda is implementable by incentives, then it is therefore implementable as well by, you see what I mean? I'm kind of confused about the theorem, because I think my understanding of the things below the statement of the theorem would be that if it's implementable by incentives, then you essentially have that it's optimal in the primal, and therefore it's more than implementable by information. It's optimal.
Yes. Okay. Very good.
So I see a disconnect between the proof and the statement of the theorem above that I'm sure you'll explain in a second.
Yes. So let me explain. I think there's a bit of confusion, because in the question of implementability, there is per se no notion of optimality at all. Some measure is implementable by a contract means that there exists a contract, and this will be a best response of this dual agent to this contract. Whether it's optimal thing to do or not, it's completely not stated. And this is why sometimes it is surprising. In the if condition, there is no optimality. There is no optimality about pi. There is no sense of optimality about lambda. It's just saying that the same measure can be possibly implemented by information and by incentive. But it turns out that if they can be implemented, they turns out to be optimal. This is why.
Okay, so I understand that that's what the statement says. What my problem is the following, that what I don't understand is that in fact, that pi is implementable by information is,
Yes.
let's say, a problem that I cannot solve. I do not know.
Yes.
What I can solve is the fact that it's implementable by incentives. So now I think what we're saying is what you need to show is that a certain pi is going to be implementable by incentives. And essentially I think your conclusion is that's all you need to do, because that's also automatically going to be implementable by information and also will turn out to be optimal. That's what I think you're trying to tell us. But the fact that it's implementable by information is kind of implied by so I don't know. I suppose
Yes.
I would understand the theorem better if you said if pi is implementable by incentives, then pi is optimal information design problem. That's what I understand what
Exactly.
the Fedor
Yes.
theorem is doing. Okay.
Yes, exactly.
So I don't understand you see what I mean? So maybe it's the wording that's confusing me a little bit.
Yes. Well, I can try to say it. I guess, I mean, it's very important to understand that there's really no connection per se between notion of implementation by information and implementation by incentive,
Right.
and about optimality. In particular, it could very well be that one measure is implemented by incentives, and it is not optimal in a dual problem, it's not optimal in a primal problem, and it's not implementable by information. It is just disconnected problems. And it so happens that the moment that the same measure can be implemented by incentives and it can be implemented by information, in that very moment, it must be that this can happen only for optimal pi.
Right.
So this is how to think of it.
But this is my problem. Is the fact is that I think what the whole point of doing the dual is that you cannot check whether it's implementable by information as such.
I see. No, but
so
yes.
that's what. So I think the route that you're telling me is I find something that's implementable by incentives. I find that it's optimal in the dual, not just implementable, but
Yes.
optimal. Then I'm gonna get is that what you're trying? You see what I mean? That's my point. Because the
Yes.
fact that it's implementable by both information incentives is actually something that I cannot check.
No, you can. Very good, very good. Let's go to the next slide. I will exactly tell how to use this method, because it's something that is something actually easy to do. That something is implementable by information and by incentives. That is something easy to do, and this is what we will be doing all the way. Exactly. So that is easy. That is easy. So let's go to the method very naturally. That how we can use this theorem to certify optimality of information structure. So first way to use this theorem is the following: guess a class of candidate information structures with measures pi star. And I mean, it can be a particular information structure, it can be a class of information structures. Now, checking that this structure is implementable by information, so this measure is implementable by information, is simple. You simply check that if players are recommended to play according to this measure, the players obey. And you can do it because you can calculate, you can do Bayesian conditioning on the part of the players, and then use first order conditions to verify whether this conditional expectation of the marginal payoff is equal to 0 or not. That is basically Bayesian updating thing that is simple to do in most of the applications that we do. And this will ensure implementation by the information. A bit trickier part in this route is actually checking whether it's implementable by contract, by incentives. Because then we need to find potentially a contract that implements this measure in the dual problem. But if we find it again for any given contract, it's easy to check, because then you need to simply calculate the best response of this dual agent to that contract, and you see, is it going to lead to this measure or not? Now, if so happens that both of these things hold, you prove that this pi star is optimal. And just to show, complete here, this is kind of direct way. You can also do it the other way, and sometimes we found that optimal, that useful. You can actually guess a class of candidate contracts, which you think will be certifying optimal information structures. And in particular, in our applications, this class of contracts turned out to be linear contracts. So we show that linear contracts are very useful in certifying optimality of measures in quadratic environments. And then you calculate best response of a dual agent to this contract onto a class of these contracts and what measures it implements. And then you verify if you recommend to play according to this measure, what you found, the players obey. If they obey, then again, you are done, because then you proved optimal implementability by the incentives and by the information. And so that is actually, it's actually quite easy to do. The bottleneck here a little bit is that you need to guess. You need to start with some measures which you think are optimal. And of course, this is quite standard in this guess to verify method. But I can give you some advice if you, on your own, you want to guess these things. So first, you can start with kind of smaller scale version of your problem and solve that explicitly, and then expect that the larger scale problem will have some qualitatively similar optimal information structures. That works, for example, for expectation polarization case. Second, you can have numerical calculations, because discretized version of that you can potentially solve numerically, and then try to actually see the patterns from that solutions. Or third, you can actually, the structure of the dual problem and of the primal problem can give you kind of hints at how optimal information structure looks like and optimal contracts, because you know that in all likelihood the optimal measure must be implementable both by incentives and by the information. Okay, that becomes a bit more clear, right? So, and I think it will become even more clear once we go back to our polarization expectation polarization application, and see how we apply this method to get very simple solution to that problem. Okay, let's do that. But before go that, let me go one more piece of theory, which I found very helpful actually in some of our applications, is that if the same contract certifies the optimality of some measure, and there is another optimal measure, then the same contract must certify the optimality of that other measure as well. So in other words, each certificate certifies the optimality of all optimal information structures. And this allows to establish universal properties of optimal information structures. In particular, if the dual agent's best response to this contract is unique, then the optimal direct information structure is unique. Why? Well, if there could be another optimal information structure, that it must be certifiable by the same contract. But what does it mean to be certifiable by the same contract? That means that the dual agents must have a best response to that contract in a dual problem that has this measure. But if the agent's best response to this contract is unique, you cannot have any other measure. So that is actually, I think, easy way to establish uniqueness of information structures. But that's not as important. Yes.
Alex, do you get any other general structural properties from the complementary slackness conditions? So somehow, one thing that I would conjecture is that, at least for non-degenerate problems, the optimal information structure is deterministic, namely the profile of actions recommended is a deterministic function of the realized state. And this is somehow suggested by the fact that it must be implementable by incentives in the dual problem. So is it right intuition?
It's in principle going the right direction. However, as you will see in this expectation polarization example, actually, there could be multiplicity in the dual problem, and in this case, there could be possible noise. But our method allows to exactly see case by case whether it happens or not. But you're right that there is a sense that if best response is unique, the information structure will be unique, but also it could be that you don't introduce a noise because the agent will have to randomize. Exactly. Yes, but let's go to applications just to give a sense how to apply all these things. So, okay, let's get back to our application. Recall that we wanted to polarize the expectations of the players. Now, recall whatever guess you had and compare to what optimal structure that we found. it turns out that for any even number of players and any prior distribution, so any distribution, any number of states, an information structure that fully reveals the state to half of the players and provides no information to the other half is optimal. So that is very simple structure, which basically is an example of what we call targeted disclosure, where you basically fully inform half players, no information to other halves. In this way, there will be no polarization across these two cohorts, which are kind of endogenously determined, but there will be a lot of polarization across these cohorts. And the optimality will be certified by symmetric linear contract, where this lambda I will be linear in AI, and I will show next couple of slides exactly how it happens. And the solution is simple, and it's robustly optimal across all even number of players and priors. So, and you need even number of players because you cannot cut the player in half. But I still find it very interesting that you have some non-trivial optimal information structure, which turns out to be robustly optimal in this sense. This is rare. This you can rarely have in Bayesian persuasion problem with single agent. And I think it provides actually very nice generalization result of Ariely, Babichenko, Sandomirskiy, and Toulouse. So kudos to Fedor, because they have that very nice paper, and they have this example where they can apply. They were studying different problems. They were studying which posterior distributions of posterior expectations you can induce, and they basically have an analog of this result for a binary state and two players. So they show if there are state is binary, there are only two players. You want to polarize their expectation, you need to provide full information to one player, no information to another player. We show by very different approach that the same qualitative result holds for any number of players, even number of players, and for any state, which was actually quite surprising to us. We didn't expect that per se to happen, but this is actually where the educated guess in our approach came from. Yes, Angel, you have a question? No.
Yes. So yeah, you almost answered it. So the educated guess is then that lambda is linear.
Yes.
Okay,
yes.
I see. And then you're gonna basically certify what is the optimal pi, no?
Yes, exactly. Let's see it next slide. You will see how it's a very natural guess. Because let's see the proof. Let's say that we want to prove that the targeted disclosure, so this is optimal thing. You provide full information to half players, no information to other half. So if you do that, then what? And this is about implementability by information, because you conjecture information structure. What players will actually do under this information structure? This is what they will do. Half of the players, those who are informed, will have action equal to the state. Right, because they know the state, they predict it perfectly. Now the other half, each of them will receive no information. The prediction will stay at the prior expectation of the state. Right. So this is the allocation. You know it is implementable by information because this is exactly the information structure that implements it. Right. And you can see that this allocation is linear in the state, right? Because this part is linear. This is just a constant. Now, by our theorem, it suffices to show that such allocation rule can be implemented by incentives. That means there exists a contract such that the agent will be willing to do so. So what is the dual agents payoff? Okay, so this is just comes from our theorem. This comes from substituting the parameters of the problem into here, right? This is polarization part. This is the marginal payoff given the quadratic loss function for predictions, right? So this is it. And now notice where the guess comes from. So we want to induce this linear allocation, and we have here almost quadratic thing. So this is quadratic, this is linear. So let's try linear multipliers, right? Because if they're linear, then it will be quadratic function, and the optimal best response will be linear. And that's what we did. We looked at the class of symmetric linear contracts. We optimized over two parameters, right? Constant parameter and responsiveness. And we found those that exactly pin down this allocation. And this is what these contracts are, right? So this turns out to be, it must be equal to that. Because if this contract you set equal to that for all players, the agent payoff can be rewritten. So here we just plugged in the Lagrange multiplier, and then you can rearrange this, and this formula would be that. This, the payoff of the agent will be this formula. This is, and again, so this is the dual agent who will observe the state and who has control over actions and who wants to maximize that. So what the agent will do? For any state, this agent is a concave and quadratic in the sum. So actually for this agent, it turns out that only the sum of the predictions matter. And there is unique aggregate best response will be equal to that. That means that any function, any allocation rule that has this feature, that the sum of predictions is equal n over 2 omega plus n over 2 that, is implementable by these contracts, so implemented by incentives. But in particular, this is exactly our allocation that was induced by targeted disclosure. Because in that case, exactly half of the players would be response equal to omega, and half of the players will have response equal to the prior state. And therefore, targeted disclosure allocation rule is implementable by information and by incentives, and by appealing to our theorem, it is optimal. So it's as simple as it is.
So Alex, this suggests that if you put this, the principal put a bit more weight on certain individuals' distance than others, then a slight modification of this would, you just change to some extent how many people get the full information, how many don't, and maybe you don't get the mean, you get something close to the mean. So it's kind of continuous in that sense.
I think it suggests that there is certainly variations to that you can analyze. Certainly, I mean, we didn't check exactly what happens, right? If you perturb some things, how it changes. But I'm pretty sure that there are modifications of this objective polarization index that can be solved by this objective. Absolutely, absolutely. It's just the one that we looked at. But one thing that I would like to highlight, and just speed up a little bit, is that here the proof hinged on the implementability by incentives of the aggregate behavior, right? And in particular, we show that this aggregate behavior must be equal to this formula, right? But this opens the door to potential multiplicity of optional information structures, because if some other information structure results in the same aggregate behavior, then even though it induces different individual actions, then such information structure must also be optimal, because it can be implemented by the same contract, by incentive. And one particular example, you can have different sets of targeted players, it's obvious, or exogenous randomization over the set. But there are more actually scope for multiplicity, because we show, for example, if omega is normally distributed in this application, then there exists a symmetric Gaussian information structure where you have some additive noises, but perfectly correlated across players, that result in exactly the same aggregate prediction behavior. So it's also exactly optimal, but it features these noises which on average can cancel out. But at the same time, by the universality proposition that I alluded to before, it follows that all optimal information structures must result in this aggregate behavior, because they must be certifiable by the same contract. So we kind of identify exactly delineate the limits of that multiplicity. Okay, good. So almost run out of time, actually. So let me skip this second application, but I think it's not a big deal, because basically we worked out now through machinery of the method, and this is just another application which we use. We apply this machinery to the question of Amazon basically providing information to firms about their demand conditions, and with linear demand structure and Gaussian shocks, we show that actually Gaussian structure is exactly optimal, and the same approach works through, and also linear contracts turns out to be certifying very different information structure, but also linear contracts turns out to be important. But let me skip for the sake of time. because instead I would like to just very briefly discuss what other results we have in the paper, and then maybe open the time to some discussion. So one of the applications I just said, it was providing information to the on the platform about demands for the firms, and in that application it was useful. It was interesting because it was basically providing information about multidimensional state. Here we have a third application which is about persuading investment, and that is the question of how to maximize project profitability if it is of certain quality, can be funded by multiple investors, and features decreasing returns to scale. And here it turns out that the optimal information structure is again simple but non-trivial. It's something what we call exclusive disclosure. This is an example of targeted disclosure in which you provide full information to a single investor and provide no information to all others, irrespective of the number of investors. So it's actually optimal information structure features even more extreme asymmetry, even though all investors are ex ante symmetric. So this is interesting. It reflects a little bit some practices of the IPO, when the startups establish good relationship with some small subset of venture capitalists, but then once they go to IPO, everybody can invest. So I think it resonates with some features, but of course it's very stylized model anyways. Good. And then we also discussed general features of certifiably optimal information structures, a little bit what Fedor asked about, because actually this certification theorem puts quite a lot of structure on what can be certifiably optimal information structures, and we discussed that in the paper. Let me briefly comment on this basically relation to the strong duality, to those who are experts on that and interested, because basically the method is based on duality, right? And the value between the dual and the primal problem is called the duality gap. And by weak duality, the duality gap is non-negative. And this is basically what we are using in our certification methods. Now, the case when delta is exactly equal to 0 is the case of strong duality. And strong duality always holds in finite linear programs. It does not always hold in infinite ones, even though in the most natural problems it does hold, of course. And for the certification method to work, we must have strong duality, and we must have existence of solutions to primal and dual problems. Luckily, you don't need to worry about it per se from the first principles, because if you construct certifying contract, this thing automatically establishes that both the gap is 0 and that the solutions to primal and dual problems exist. So in this sense, either all optimal information structures can be certified or none of them can. And right, that is very important slide because it goes back to the title a little bit. So title is information design smooth games, because so far we focus on concave games. Why is more general title? Is because we believe that actually the same method can be applied more broadly. The thing is that in concave games, the first order conditions are necessary and sufficient. However, our analysis can be applied in any smooth game, that is a game in which your own payoff is differentiable in your own action. And in a smooth game, the first order conditions are clearly necessary, right? This derivative around recommendations must be equal to 0. If not, you have profitable deviation. However, they might not be sufficient. Now, what you can do if you have some non-concave game, you can basically view our primal problem as a relaxed information design problem, where you keep track on local deviations. And if you solve that problem, and this relaxed optimal information structure, under this optimal information structure, players are willing to follow recommendations. That is, if you check global incentives under the optimal information structure, they're still willing to follow recommendations, then the structure will be optimal in the original problem as well, simply because it's optimal in the more relaxed problem, and it satisfies all constraints in the original problem. So, and I think that could be a helpful way to study even broader class than concave games, even though I think a lot of economic settings fall in the under the umbrella of non-K-clues. Okay, good. A bit out of time, so but we're right to the summary. So what we did in this paper, we presented a, we believe, tractable solution method to information design in games. We studied the dual problem as a adversarial contracting, and this our basically our method that we propose is based on optimality certification of optimal information structures. And we show that this method is actually very tractable, and we apply obtain novel solutions to information design problem in very classic economic settings. And we establish optimality of some natural and simple classes of information policies like targeted disclosure and Gaussian information structures. And I think more importantly, kind of looking forward, I think the analysis paves the way for more applications of information design in games, which seems to be the natural next step in a Bayesian persuasion and information design literature. And with that, thank you very much.
Okay, Alex, thank you very much. That was very interesting. I wanted to ask Mallesh and Fedor if they had any more questions or comments, and then we'll open it up for everybody else to ask questions if they have any. Please, guys, whichever one wants to start.
Fedor, you want to go? Yeah, this is going to be you first. Let me just start with something because maybe I should just read the paper, and it's been on my list. But I guess I'm curious, like, like the theorem is cool. What other cases give you, like, because you need to actually churn this dual machinery. So part of it comes down to when the dual machinery actually gives you something interesting and interpretable about the optimal solution. So I guess you were going to go over a second example. Do you have, like, I don't know if this is something you can formalize, but is there some class where you can broadly say within this class we'll always get interesting answers for the optimal? I don't even know how to form that question, actually.
Okay, let me think a little bit. So what I can tell you is that okay, maybe actually it's a good way to get briefly back to that application that I did skip. So this is an application when there are two firms and we have normally distributed shocks, and then what we do show that an optimal information structure turns out to be Gaussian. That is, so if we look here, that the optimal recommendations, the original states are normally distributed, and the optimal recommendations to players, that is will be the price that they set, turns out to be linear in these states. So, and for that, it is important that the states are normally distributed. But along the way of us proving that result in this setting, we basically show that this linear, okay, let me actually show, and that we certify optimality of this structure by linear contracts as well, and we show that this linear contracts turns out to be optimal certificates in a large class of quadratic games with Gaussian uncertainty. And I think this is already very interesting because a priori, even though you start with Gaussian information, Gaussian states, a priori it is not obvious that the structure that you're providing will be also Gaussian. And this, in particular, not only Gaussian, it will be also noise-free. That is, the actions will be recommended without any additional normal noise. And this, so our proof allows us to basically provide the proof of optimality of Gaussian structures in this class. So this is just one class we elaborated, but I think in some sense this is up to researchers trying to see how these tools are applicable, and this is why we added, we could add more applications, or we could elaborate on applications that we have. We just paper, you can't go beyond the limits, and I think it's also not the point. I would like other write nice papers by using this approach, because I believe it is. Because we started with one applications, and then we got the questions. We came up with another application, then we came up with third application. But I think I think there is large scope. It's my really personal kind of, after working with these things, I think it is very useful. And the thing is that there are not many alternatives how to solve information design in games with continuum actions. In fact, I know none. I mean, I know there are some ways to do it in Gaussian things, but I think it does open a large area of applications, I think. But we don't have, so beyond this normal structure, which is buried in a proof a little bit of the appendix, we don't have results for classes of problems. I mean, we could potentially.
Okay, Fedor.
Actually, I have many questions, but let me just focus on one that is maybe the most philosophical. So, kind of one of the most mysterious and puzzling conclusions from your approach is that somehow it allows you to avoid all these complications that you mentioned, the fact that in general games, the whole belief hierarchy matters. And somehow your approach is not sensitive to that, to the extent that you get the same structure of the duel, no matter whether you had strategic externalities or you did not have them. So you end up with either equally simple or equally hard problems, but somehow you just avoid this difficulty. Do you think that this is somehow related to the fact that maybe in concave games, even if you have strategic externalities, even if higher order beliefs matter, they matter in some very particular way? Somehow, not the whole belief hierarchy, but maybe a certain, I don't know, a certain particular functional, like in the example that you showed us, where what actually matters is this aggregate action. Do you think that it's something general? This is the reason why your approach is not sensitive to higher order beliefs?
Yeah, that's a great question. So let me address it in two parts. So about high order beliefs, importance of high order beliefs. I think it's the question of high order beliefs bypassed already directly by looking at direct recommendations, because basically, if you use belief approach and think about what beliefs you induce, then you need to carry around the whole belief hierarchies. Now, if you do go back to Byers and Bergam and Morris, there even the primal problem doesn't anymore feature any high order beliefs, just because you kind of recognize that this action that matters and incentives that they can verify, and in a small scale problems you can just solve that. So I think that the question of high order beliefs bypassed by just alluding to revelation principle. But because of that, you have to use different approach. It's not belief-based approach. You need to think about distribution of actions that you recommend. But then this approach in large-scale game is challenging, because you have this continuum of possible incentives, right? You need to keep track around, and for that, duality turns out to be helpful. Now where concavity plays a role. So I do not think that a priori in concave game you have some very simple equilibria, for example, right? Because if you think about, I mean, if there's full information, right? And we discussed a little bit. Yes, it could be the games with potential, etc. But given that there is incomplete information, and in fact you can design that information that you do. Imagine you provide some strange asymmetric information across players, even though they have concave payoffs. Having concave payoffs only buys you that the incentives, the deviance constraints are captured by these equations, and this is only what we need. But it doesn't tell you actually what system of these choices will form an equilibrium, and it can be very complicated. So I do not. I think this is the only thing where we use concavity, and this is why I think it's also generalized more generally for smooth games. But it is true that, you know, for some games that we study, clearly there is some structure that leads to optimality, for some nice structures to be optimal. But it's not just concavity; it must be something else. And I think it's not. There is. I cannot pin down just yet. And it's true that in belief expectation polarization application, we have that there's this, it's basically you have this statistic that is uniquely optimal. But for example, already in this application, which I didn't cover, you have uniquely optimal information structure. So then that is very different. But it's something interesting to think about, I think.
Sorry, guys. Sorry to interrupt a second. We because it's time to maybe interrupt the recording, and also Mallesh needs to go. So I just wanted to thank him publicly before I think he's gone.
Yes, thank you, Mallesh. Thank you very much.
But we can continue without the recording, and